Okay, so let's welcome our first speaker, second speaker in the afternoon, Professor Lu Wang from Yale University. And the title of her talk is Recent Progress on Self-Expander of Mean Curvature Flow and Applications. So let's welcome.
Um, so first of all, I would like to thank the organizer for their kind invitation, and I've been greatly enjoyed the Congress, and also thank everyone for attending my talks under such weather condition. So for this talk, I will start with introduction to a mean curvature flow. So let's take some hypersurface sigma in the European space. So at each point on this hypersurface, so we can choose a normal mu x. Right? So this is the tangent space. So mu x is the unit normal to sigma at x. Okay. Right. So then we define the mean curvature hx to be the minus of the divergence of mu x times mu x. So namely, we take the divergence of this unit normal, so along sigma, so and take a minus sign, and so define this as the scalar mean curvature, and the direction of this mean curvature is given by the unit normal. Okay, so this is the mean curvature. Right, so now each point we have this mean curvature, and then let's imagine that each point on this sigma is going to move by the velocity given by this mean curvature. Then it's going to form a one-parameter family of hypersurface. This is the define the mean curvature flow. Okay, so take a family of hypersurface. So it is a mean curvature flow. So if so velocity is given by mean curvature. Okay. So in this talk, we're also going to use MCF as a short stand for mean curvature flow. Okay. So so let's consider some special case first about mean curvature flow. So for instance, one can think about initially we have our hypersurface sigma given by a graph of a function u. So this means that the parameter is this way. Let's use another letter. Okay, so y it is Rn. Right, so then the initially sigma is given by this graph of a function u. Okay, so then this mean curvature flow starting from sigma it is given by a graph of u t. So this U of sub t is going to satisfy that. So U t equal to right. So in this special case, so when we start from entire graph, of which means that the graph over the entire one dimension lower plane. So then, under suitable assumption, for instance, assume the graph is actually an ellipsis graph, then one can show that the mean curvature flow, starting from this such initial data sigma, remain being a graphical, and so it satisfies this equation. So this is the quasi linear parabolic equation. Right. And I should say that this is actually and so now you have a basically a family of function u depends on this parameter t, satisfy this PDE and with initial data given by this u of y. So this is actually a well-studied nonlinear PDE, right? So okay. So from geometric viewpoint, so this was first studied by Eicher and Quiskin. And basically, they show that this is so the solution to this PDE with this initial data is actually exists for a long time, given the initial data u is actually an ellipsis function. Okay? And moreover, so they show that assume this u infinity. Okay? So then we can consider the asymptotic limit of this flow as t tend to infinity. So a priori it may actually go to infinity. However, if we try to rescale the solution suitably, so we can get some non-trivial limit. So namely, we can consider the following. So u y. Okay, so this is going to converge to some so it is going to converge to some solution v of y as lambda tend to. I think I'm probably going to as lambda tend to 0. And this v y, it is going to satisfy so v. So in other words, so you see that this v is going to be also a long-time solution to the mean curvature flow, but satisfy this additional symmetry. So geometrically, it just means that so you see that v is going to be self-similarly expanding. Okay? So because of this symmetry condition, you see that so even though it's defined on the space-time, but at the t time slice is completely determined by the t equal to 1 time slice. So we only need to worry about so v of 1 and y, right? So such v is called self-expanding solution to mean curvature flow. Okay. Right. So what this tells us basically, it shows that so under certain growth condition on the gradient of this function u, one can see that at the long time behavior of this mean curvature flow, entire graphical mean curvature flow is modeled on this self-expanding solution to the flow. Okay. So this means that, so I won't say that again, right? So you have seen this, right? So, okay, so, and so basically the hypersurface defines by this V. So and let's see, consider Y. It is a self-expander. Right. So this is one way that we see that the self-expanding solution or self-expander arise in the study of a mean curvature flow as a model of the long-time behavior, right? So next, I will going to mention another way to see how this self-expander arise. Okay. So here we consider entire graph is non-compact hypersurface in Euclidean space, right? So it's also interesting or more interesting to consider initial data which is given by a closed hypersurface, right? So for instance, right, so one can consider, let's take a sphere, right? Right, so if I take a sphere in 1+1, right? So suppose this sphere is has a radius, say, r, right? So then at this point in the sphere, so the mean curvature, it is given by minus n divided by r times this, right? Because we know that so the normal at the point on sphere is always given by x divided by the norm of x, right? So and you take a divergence of the normal, right? So then you easily see that you get this quantity n divided by r, right? So in particular, this tells us that so at this point, so the mean curvature vector is going to point towards the center of the sphere, and the magnitude is given by this number n divided by r, right? So this sphere is going to shrink under the flow, to apply mean curvature flow, right? Right. So at later time, you're going to see another sphere, but with a smaller radius, right? Because the point actually move inward, right? So on the other hand, from this formula, you see when the sphere has a smaller radius, then you get a bigger magnitude of the mean curvature. So which means that the velocity of the point on this moving sphere become larger, right? So then you actually shrink faster. And then in finite time, so you're going to see the sphere just collapse to the center of the right. So and when this happens, so let's take extinction time. So this is always finite. When this happens, you see the r is actually become 0. So which means the magnitude of the mean curvature become infinite, right? So then your flows stop being well defined, at least in the classical PDE sense. Right? So you see from the equation that the velocity is exactly go to infinity as it's a convert to the point. Right? So, and you can also consider examples like a cylinder, right? So, which is the product of a sphere with the RK factor, right? So then you just see that, so the cross section of the cylinder is going to shrink, and the product structure is remained, and then you see in finite time, so the cylinder is collapsed to its axis, right? So there's another example, right? So this example shows that so when you have a closed hypersurface in Euclidean space, so then the mean curvature flow of such closed hypersurface may develop singularities in finite time, which is contrast to the situation when we start flow at entire graph, right? And indeed, so an important fact is, so by avoidance principle, so this is nothing but just like a strong maximal principle in parabolic PDE. For parabolic PDE. Right, so a mean curvature flow starting from any closed hypersurface must develop singularities in finite time. Okay, so here the key is that we need to make sure the hypersurface is compact without boundary. So the way you see it geometrically is like so. You see, can I draw here? If I draw here, I can. So you take any closed hypersurface sigma. Okay, so right, so then you can unclose the sigma by a very large ball, and with boundaries given by this sphere, right? And now the avoidance principle tells us that so the flow of sigma and the sphere should remain disjoint unless one of them becomes singular, right? So we already know that the sphere is going to collapse to the center in finite time, right? So then this means that the sigma must develop singularities before the class of the sphere. Okay? So this shows that so the singularity must form. And so the next step is so to try to understand how the singularity forms, right? So basically, when you see the singularity happen, so then you try to zoom in the flow near the singular point and take a limit and see what limit you get, right? So it's a typical blow-up analysis. Like you've seen in many nonlinear PDE theory, right? So here is just like a geometric PDE. Okay, so basically, so I'm not going to give the details, so I'm just going to see that this means that you zoom in the flow near a singular point. say some point x0, t0, and take a suitable limit. Okay. Right. So then this is going to produce another mean curvature flow, say gamma t. So but with a special structure, namely, so the gamma t is equal to gamma minus 1. So in other words, so you're going to get another mean curvature flow, but with this additional scaling property, namely self-similarly shrinking, right? Okay. Right, so ideally, so you want to maybe try to see that if we can classify these solutions, right? So if we can classify all this, I should also say that this is called self-shrinking solution to mean curvature flow. Right, so in other words, this means that self-similar shrinking solutions that model the singularity formation of the flow, right? So ideally, we would like to classify all of them, but this is virtually impossible. Classify self-shrinking solutions. Right, so because we have many examples, right, so basically we've seen some trivial examples in the previous board, right? So I just erased the spheres, right? So there will be examples, and plane is also example, and cylinders. So if we are actually in the situation that this is only examples, then we're in a very good situation. So because this has a very simple geometry, right? So and it's easy to study, right? So however, so there's much more example than these simple ones. So perhaps, so besides these simple ones, the first rigorous example is this Argand torus, so which is the rotation symmetry torus. So here is the curve, and you just rotate them. Right? Not very good at drawing. I'll just embarrass myself. So this will be the generating curve, and this is the rotation axis. Okay. So I should say that so this Argand torus is not given by an explicit formula. So it's constructed by using some shooting method. Okay. So and until now, we still don't know the uniqueness of this Argand torus in the class of rotationally symmetric self-shrinking solutions, because so they are constructed in an inexplicit way. Okay. And you think, okay, so maybe that's all we know, right? So maybe you only have a rotation symmetric examples, right? And it's actually not the case at all. So we can actually construct an infinitely many example. Basically, now we know that for every genus G, there is a self-shrinking solution of genus. So this is, of course, in R3, right? Because we talk about genus, right? So for every genus D, you're going to find some surface of genus D, and then you apply this dilation, you get a self-shrinking solution to the flow. Okay? And for large G, this is constructed by Ablias. Molar and more recently also so basically, so even in R3, so we get actually infinitely many examples of these self-shrinkers that potentially could be singularities in the flow, right? So these examples basically tell us that so it's impossible to classify these shrinking solutions. And so what's related to the talk is in particular these examples. So I should also see that this example is actually non-compact. So they're going to have one end that asymptotic to a cone. So from this set of example, you see that so a large interesting class of singularities, they are actually modeled on this non-compact asymptotic conical shrinkers, right? Right, so, okay. And this is actually not complete. So there, after this work, so there are more and more examples are found. So, but due to time limits, I just mentioned some of them. So, okay, right. So before, so if we only have this kind of a cylindrical singularity, well, so we may actually try to develop some surgery theory analog to the Ricci flow case to continue the flow through the singularities, right? So now if we have some singularity models like these ones, right? So then we can't actually just try to do something like a Ricci flow case, right? So at least in 3D Ricci flow, so there's no such analog singularity models, right? And so then one needs some new technique or idea to try to deal with the question like how to continue the flow through singularity that are modeled on such a self-shrinking solution. Right, so we've known that when we zoom in the flow near the singular point but before the singular time, then we see that the self-similar shrinking solutions appear, right? Suppose we have see one of these shrinkers appear, right? So maybe draw something like this. So maybe this is some shrinker. So in other words, I mean that, so if we consider this gives me a curvature flow. Okay. Right. So think about, so then this is the t equal to minus 1 times less, okay? Right? So because then you get sigma itself, right? And under the mean curvature flow, it's self-similarly shrinking, right? So at a later time, you're just going to see this, right? And you see that you try to bring the infinity into the compact region, right? So, and at the time t equal to 0, so then we're just going to see the cone, right? So this is the asymptotic cone to sigma at the space infinity, right? Is it clear? So we have some like shrinker, right? So sigma that asymptotic to the cone at infinity, right? And versus shrinker, so it's a self-similarly shrinking under the flow, right? So, and when t equal to 0, you think about t tend to 0, right? So then this means that you're going to get a cone, which is the asymptotic cone to sigma at the spatial infinity, right? Right. So now the question is like, so your classical flow is not well defined at t equal to 0 and beyond, right? Because you clearly see the curvature is a blow up, right? So now the question is like, how are you going to actually continue your flow from this point, right? So how are you going to resolve this singularity at the vertex of the cone? So to resolve cone singularity, we need these self-expanders. Right, so what is this self-expander in this setup? It just means that you have gamma t gamma. And this is the mean curvature flow with t tend to 0. So this is the actually tend to this cone. Is it clear? So basically, so you can think about for now you think about the cone as the initial data, right? So instead of have a smooth hypersurface, now you have a hypersurface which is given by this cone with this singularity at the vertex, right? And now you're wondering, like, now if you have a singular initial data, how you actually define the mean curvature flow starting from a singular initial data. So there are many, so I'm not claiming that, any mean curvature flow starting from the cone is given by the self-similar expanding solution. But on the other hand, so this self-similar expanding solution give you a smooth solution, possible smooth solution with initial data coming out of cone. And moreover, if time permits, we can discuss some forward monotheistic formula to see that actually in a large class of situation, we will see that even the non-self-similar expanding solutions coming out of cone is actually modeled on these self-expanders. So namely, so you can do some forward blow-up analysis at the vertex of the cone, and then you take a limit, then you see the self-similar expanding solution appear as a limit. But for simplicity, right? So say if you just try to smoothen out this cone singularity, right? So of course, if you can find a self-similarly expanding solution to do the task, that would be simple than try to find the general ones, right? Okay. So then to summarize, right? So right now, so we've seen that so self-expanders, they model long-time behavior of mean curve flow starting from entire graph as in the beginning of the lecture, right? So the result of Acker-Huiskin, right? And it's also provide model the asymptotic behavior of a flow that's coming, emerging from a cone-like singularities, right? So that's why we're interested in this class of solutions. Right. Okay, so however, so these self-expanding solutions, they are actually highly non-unique. So there's an example by Trop Humanen. Why? Sorry. Okay, so they study rotation symmetric cone, and they also has a reflexive symmetry about the hyperplane. Okay. And so when you let the cone angle become very large, so then you begin see many expanders coming out of cone. So you see some yellow ones, so they are just like a topological disk that coming out of each component of this cone. But you also see some connected self-expanders. So basically, they show that there exists more than one self-expander coming out of a cone. Right, so in other words, you see that so issue for the resolution of the cone singularity is like, so given the cone, you may have more than one way to actually resolve the singularity, right? So then it's unclear like how, naturally you want to say, okay, so is there like some selection principle, right? So this is certainly an interesting question, but right now it's completely open. Okay? So inspired by this non-uniqueness phenomenon, so in collaboration with Jacob Bernstein, so we don't study the uniqueness of these self-expanders. Rather, so we try to think about the whole space of self-expanders and try to see if we can prove some structures on the space. So for instance, so from this motivation, right? So it's natural to consider asymptotic conical self-expanders, right? So and then we asked, okay, so whether there's some like manifold structure on this space of asymptotic conical self-expanders. Okay, so. Right, so let me first see one. Bernstein. roughly speaking, we show that the space of asymptotically conical self-expanders it is smooth manifolds of infinite dimension. Right, so basically, so to prove this type of result, we just basically try to compare with the work of White on this space of minimal surfaces with boundary. So basically, we just basically think the asymptotic cone as this boundary at infinity, right? So the expanders, because it is a flow, so then you can see that it's completely determined by this time t equal to 1 slice, which is the gamma, and this satisfies some elliptic equation. So then, so if I look at the gamma, right? So it satisfies so this mean curvature minus is equal to 0. Okay. Right. So this is the Euler-Lagrange equation for this functional. We call it E. Right, so then you can compare with, so minimal surface, they are just given by h equal to 0, which is the Euler-Lagrange equation for the area functional without this weight, right? So then you can just basically follow the strategy of White's work, but then you only need to work on suitable function space to prove the estimates, right? So correspondingly, right? So this is our first result in this direction on these self-expanders, right? So after proving this example, right, so it's not completely satisfying because in the example I just showed you, so this is a given cone. So then you still have a non-uniqueness, right? So this tells you that you can, when you vary the cone, so you see how the expander actually corresponding varies, right? So then to actually understand these examples of Agnen-Trop Ullmann, so we also need to try to study the space of self-expanders asymptotic to a given cone. So you fix cone, and then you look at the expander asymptotic to this cone, and you try to see can you actually find some interesting structure among these expanders, right? Okay, so okay, so the next theorem which is also with Jacob Bernstein. So we basically prove some mountain path theorem for this is right here, mountain pass theorem for expanders. So basically, you can see that if you have two self-expanders, say gamma plus and gamma minus. So gamma plus, gamma minus are disjoint, strictly stable self-expanders. Okay. So we've seen that the expander, they are critical points for this functional, right? So now you have two strictly stable critical points to functional. So like in the calculus, you should expect to get a saddle point for this functional, right? So now, of course, it's not as trivial as in calculus because the space we consider for this functional is infinite dimensional, right? So then we can't just cite a calculus theorem to prove this, right? So, but on the other hand, in the same spirit, you can prove this type of theorem. So, namely, so then in between this gamma plus and gamma minus, one can find a third expander. Oh, I forgot to say that the all asymptotic to same cone. Okay, so same cone. Okay. Expander gamma, which is not equal to these given ones, they are trapped between gamma plus and gamma minus. And the third theorem is drawn with Le-Dian-Chen. Right, so given the cone, right, so you have maybe more than one self-expanders and they are critical point to this functional, then we divided them into two class, stable and unstable ones, right? And so in the generic situation, so the stable ones imply strictly stable. So then, between the two strictly stable ones, you can find the third one. So indeed, you can show that the third one generically has to be unstable one, like the heuristic we explained, right? So when you have a mountain pass theorem in the calculus, right? So this generically unstable. So the third theorem tells you that when you start from unstable one, how is actually connected to the stable critical points, to the expander functional. Okay. So again, right, so in the calculus, when you have a saddle point, right, so then you can find the unstable direction, right? So then you perturb along the unstable direction, it should actually flow to a stable critical point, right? So that's the heuristic, right? So then we just basically justify this heuristic picture. Okay. So namely, so again, so I will just draw a picture instead of write all these words. So let's take unstable. So this is my unstable expander. Asymptotic to a cone at infinity. Right, so then this expander going to divide the whole space into two parts, right? So then on either side of this unstable expander, so you can find so this gamma plus and minus, these are stable expanders, asymptotic to same cone. Okay. Right. So they lie on either side of this gamma. Okay. And so then the gamma plus and gamma minus, they basically bound the regions, right? So in these regions, then you'll be able to fill in the regions by the gradient flow lines. Like this. So these are gamma t plus, this is gamma t minus. So basically, so you're going to have gamma t plus minus t. Okay. So this gamma t plus minus converts to gamma as t tend to minus infinity, and gamma t plus minus converts to gamma plus minus as t tend to positive infinity. Is that clear? So basically, you have an unstable expander. So then you can find the suitable, basically the way we construct this, we call it eternal solution, is coming from a approximation process. We first basically perturb this expander to either side so that it has a suitable curvature condition. So then we can begin flow the perturbed surface, and then to find this limit gamma plus and gamma minus. And then we take a perturbed parameter epsilon tend to 0 to get the eternal solution like this one. So geometrically, what you see that, so this right lines is going to fill in the whole space between this gamma plus and the gamma and the gamma and the gamma minus. They are actually moving monotonely. So here the only caveat is that this gamma t plus and minus flow, so they may not be actually smooth flow. So they may actually have so this is a gradient flow. So gradient flow for this functional E. So they may actually have cylindrical singularities. Okay, so now if we try to look at this theorem 2 together with theorem 3, right? So generically, right, so suppose we have right here, suppose we only, actually, so let me make a big assumption. So suppose given a cone that will only have two strictly stable expanders, right? So this gamma plus and gamma minus, right? So from this mountain path theorem, we find this unstable one, gamma, right? And then now use this theorem 3, right? So in between, we fill in this domain between this gamma plus, gamma minus by this almost regular flow lines, except for some cylindrical singularities, right? So then this gives us some like, I would like to compare with this baseline diagram for the autonomial ODE system, ODE, right? So when we have an ODE system like, say, dy dt, right? So then you would write a line in y-axis, right? So mark A1, A2, A3, right? And then the flow lines, then maybe this A1 is stable, unstable. I may not be correct. So you draw these pictures, right? So the flow line is like this, right? So now for this picture, you just compress this gamma plus and gamma minus gamma as this critical point A1, A2, A3, right? So, and this flow lines, this gamma T plus and minus, like the region in between, right? So of course, so the difficulty is really lie in all this detailed analysis, right? So here we have to deal with some PDE, right? So not just ODE, right? But on the other hand, so because we have this gradient structure, right? So the rational structure, right? So then one can also think about it as some ODE in the infinite dimensional function space, right? So that's how you can, heuristic, you can think of why this theorem makes sense. Okay. So yeah, so I think so my time is running out. So so I think maybe I should just stop here and open to the question session. Thank you.
Thanks, Professor Wang, for her very insightful talk. So, any questions from our audience? Yeah. Raise your hand if you have any.
For the self-expanders, are there any other type of singularities that can develop?
For the self-expander. Oh, so very good question. So I only consider smooth self-expander, but obviously they are actually singular expanders. So for instance, we have the equations given by this, right? So I could consider minimal cones. So this means that the mean curvature is 0 and the normal is also 0. So this also example of expanders that can possibly develop. Yes. On the other hand, I don't actually know singular expander that are not minimal cones. So the example people constructed are usually just smooth expanders.
Any further questions?
Oh, you mean expander? All expander actually has to be non-compact. Yes, there are no compact expander. All the expander has to be non-compact. But the only thing I'll cheat a little bit here, I assume is asymptotic to a cone, where the cone is actually has a smooth link. But a priori, so it may not be the case. It may actually asymptotic to a cone with non-isolated singularities. I'm dealing with the simplest situation here.
Yeah. More questions?
Can you comment a little bit on the stabilities of the self-expander? Any explicit example and the notions of stability? Thanks.
Yeah. So yes. So I should have mentioned this important result. Basically, given any cone, also imminent. So you take any cone. Let's see the cone is in Rn plus 1, and also only singular at the vertex of the cone. And let's also assume that for simplicity, let's assume n is less than or equal to 6. Okay, so I will explain why we need this. So basically, they show that you can always construct. Actually, not write in this way. It's okay. So let's just write in this way. So you can always construct E minimizer. So in particular, this tells you that it's stable. So basically, for any cone in low dimension, you can construct stable expanders. And you can also show that if there's more than one expander coming out of this cone, you can construct at least 2 stable expanders. Yeah, so it's a very, if you also know a little bit about the shrinker series, so there's no stable shrinkers. So it's an interesting contrast to them.
Any further questions? Maybe I want to ask a question. So about the connectedness of your manifold of the self-shrinker. So if the cone is if the cone is disconnected at the infinite, well, the manifold also.
Not necessary. So let me just record this this example. See, we have a very fat double cone, like this one. So almost like collapse to the thing, right? So in this case, you can actually construct some connected self-expanders. So they're like annular.
Yeah. Actually, my question is about the connectedness of the space of self-shrinker.
Oh, the space. Oh, no. Definitely not necessarily connected. Yeah. Oh, so when you say the space, you mean the space of all expanders, yes, right? Yes. So then we don't know, because when I state that's the manifold structure theorem, I cheat a little bit. I should actually prefix the topological tab. So even in that case, I think to address the connectedness of a modular space of an expander, that is a much harder problem. Usually it's not the case.
Thank you. Yeah. So I think we can stop here. So let's thank our Professor Wang again.
Yeah. Thank you.
So the next lecture begin at 3:30.